Well, I guess it's time for our next talk. We'll have a homomorphism.
Thank you very much. I want to first of all thank the organizers for organizing this workshop. And actually, I'm very happy to be here because when I came to the US, this is actually my home. California is a second home. So it gave me an opportunity to come back here to say hello to my family here. And also to say thank you to them for accommodating me for 2 years, right?
Something like that.
Okay, so what I'm speaking on today is a joint work with Themba Dube. We're on the torsion ideal of a homomorphism. So what are we doing? We look at what was defined as the torsion ideal of a homomorphism. Since we work in algebraic frames with FIP, specifically in the frames of radical ideals and the frames of Z ideals, we looked at this and we decided, okay, let's see how it is defined. Then let's take a look at, see an analogous definition in terms of category of FIP frames, which I'm going to define there. Then we compare. How do they relate to each other? So most of the things you are going to see there is the relationship. And also, we defined something more general than the definition that was given. All our rings are going to be commutative with non-zero identity. Ring homomorphisms preserve the identity, and the category of rings with their homomorphisms is called, we're going to represent it by C ring. Each frame, the objects of which are algebraic frames, in which, of course, the FIP there, bit of two compact elements is compact, and the morphisms are the frame homomorphisms, which take compact elements to compact elements. Some of these things, I missed a lot of the talks because of my drama with my flight. So some of the things will be the definitions. I believe they've already been defined. So maybe I'll be very quick in flipping through the slides for familiar things. But of course, I included a lot of familiar things just for us to recall them in case we've forgotten them. So of course, I know this audience is much higher than some of these things. Okay, it's not.
You gotta click on the screen so that it can start.
I guess I messed it up.
Oh, okay. Thank you. Right. So actually, this definition, we took it from this article of Dobbs and Picavet, straight rings. That's where we got the definition. And how did they define? They said the torsion ideal of a ring homomorphism vary from A to B, denoted by that, is given by this requirement. So if you take a B in that, B lives there. If and only if the product of B with the image of A under varpid is equal to 0 for some non-zero divisor A in A. So that is how they defined it. Okay, so now, before we continue, we want to recall some few definitions that we will use. We recall that an element A of a ring A is said to be prime to an ideal I of A. If for any X in A, the containment, the product lives in I, implies that X is in I. Of course, the contraposition, X not in I, implies the product not in I. So, from the definition, we could see that an element of A is a non-zero divisor if and only if it is prime to the zero ideal of A. Now, the torsion ideal now consists of those elements B of B such that we have that. Please, this notation, we're using this. We're using this to denote the zero ideal. It's not unique. Of course, normally in set, we say that is just a set with zero, but don't look at it that way. We're saying that is the zero ideal. And of course, this is what we are going to be using more. The notation should have been like the ideal generated by zero. And we use our, that's the standard. But for convenience, we are using this. Oh. So it should have been something like this, right? But for convenience, I'm going to go back.
Oh, yeah, I was making sure the camera could see you, but
Oh,
it does.
doesn't need to see me. Okay, so just bear with me since we are using this notation. We're going to stick with that for now. Of course, this is the definition of a radical ideal, which I think we are all familiar with. Also, we have the definition of the new radical, which we are going to use a lot. So, of course, we know if the new radical is the zero ideal, then A is said to be reduced. These are just information that we are recalling. Now, what we did first was, let us replace the zero ideal with the neo radical. So you get something a little bit more general than what they are having. So if we have that, and also let us replace our non-zero divisors with elements prime to the neo radical in the definition of the torsion ideal that was given. So if we have that, we can now write our new definition as this. B lives in that torsion ideal if and only if the product is in the neo radical P for some A in A, which is prime to the neo. Okay. Now, all these stories, we're familiar with them. Like I said, that should have been the notation we should be using, but for convenience. So if we write what we have there is the ideal generated by S. And if your S is finite, we're going to just rewrite it as this. Okay, and of course, we are familiar with the annihilator of S is the set of all elements in A such that the product with the elements in X is equal to 0 for every X in X. This is the definition of the non-zero divisors. So we're going to write them like this. So this is how it is defined, the non-zero divisors. Now, since we've looked at a lot of basic information that we need in terms of the ring part of it. Now, let's introduce our lattice, read A. So, read A is a frame, and the partial order is by inclusion. Most of us are familiar with that. So, it's an object of fifth frame. And of course, what we normally do, we will denote the bottom element by this and the top element that, but at times we might use other notations like the box of 0 for the bottom element of read A and box 1 for the top element of read A. Right, and of course, this is the basic, is a radical ideal. So most times we might not be using this notation. For the radical ideal generated by A, we might just be using this box of A to represent, to make it easier. Now, what are the compacts? Compacts, radical ideals, of course, we know how they are defined. So I is compact if and only if you can write it as these joints where you have the elements as finite sets. Okay, an observation, of course, which you are familiar with is this. And since we know the frame of radical ideals is a coherent frame, we know that the meter of two compact elements is compact, it is a compact. So this is covered with the properties of the frame of radical ideals. Okay, so the functor read going from commutative rings with identity to phi frame. This is how it maps. For any ring homomorphism, we have a coherent map. So it takes compact to compact. And of course, this is how it maps, and the right hand joint is given by this. It's something that is familiar, but I just wanted to include it in the slide so that you recall them. When we want to use them, it becomes easy for us to see how it works. Okay. I'm recalling this definition of the torsion ideal again, because there is something else I need to display now, whereby we need to see how it connects. Now, like I said, we looked at the ring definition given by the authors of street rings. Now, of course, we know every frame homomorphism induces every ring homomorphism, I beg your pardon, induces a coherent frame homomorphism between algebraic frames with phi. So the question now is, okay, as we are looking at the algebraic frames with phi, let us define a torsion ideal for the coherent map that is being induced. So now, how do we define it? So for each morphism, a coherent map, we have an ideal T of H of the lattice of compact elements of the podomain, and an element tau sub H of M in such a way that, subject to my constraint, you have it. You have all this going on here. Now, the question is, what is this tau of H? Don't worry, we are going to define what it is, and we're going to see how it is related to this torsion ideal, where H is a coherent map. Okay, now, if our rings are reduced, you have that your TH coincides with this torsion ideal, coincides with this element here. But if your rings are not reduced, you may not have that. Okay. Some other definition that we need before we proceed, we start with the definition of a unit. A unit in an algebraic frame is a dense compact element. Actually, we're saying in algebraic frame, but we already know that, of course, in any frame, you have a unit. So you have, but since we are in this context, we are working with algebraic frames, that's why we said an algebraic frame. But of course, the definition holds for any frame. Have that. Okay, so the set of units in our frame would denote by U of L. Now, if the frame has no units, then if the set of units, if it's not empty, then L is said to have units. But at times it's possible that the frame may not have units, right? So if it doesn't have units, we're going to look at what happens there. Now, because we have that the meter of two dense elements is dense, so we can have, if we meet two units, we have each of them as a unit, the meat is also a unit. We know we are working with algebraic frames, so we have the meat of two compact elements is compact. So of course, with meat of two dense element dense, then that is also true. Now, this is what we have. We are defining the T of H properly now. So if we have this coherent map between algebraic frames with field, the torsion ideal of H is actually this set. The first part, this is how it maps. So the analogous definition in terms of algebraic frames with field, this is what we get once we translate what we have for the rings. So this is the case if L has units. And this is equal to 0, the 0 ideal, if L has no units. So now, what is the relationship between the torsion ideal of H and the tau sub H? Because we said the tau sub H is an element of reveal. So actually, it is written as the join of the torsion ideal of H. So that's the connection. Now, we see later on that this join actually is a directed join. Now, the first little result that we have is that if H is a morphism in fifth frame, then tau of H is an ideal of the lattice of compact elements, because that we use to denote compact elements of M. Of course, if we go back by definition, once we look at the definition, how we define the torsion ideal of H, we see that 0 is there, it's a dance set. So that follows. So the only thing we need to show is that for any two elements I take there, there's always something bigger than each of those. There's as an ideal, so I can get something bigger. So that is exactly what we showed. And of course, if we look at this, it went through because this is definitely, this is smaller than this. Joining this is smaller than this, but this actually by definition, what we have before is 0. So we've been able to show that actually it is an ideal. Okay. Now, we are recalling these ideals again. So the torsion ideal, in terms of the torsion ideal of B with respect to VRP there, and also this element of read B. So the question is, how are they related? How are these two elements related? And that is what we're going to be looking at. Now, we already know this is an element of read B, so definitely is a radical idea. But this may not necessarily be a radical, of course. It may not be a radical idea. So the question is, when is it a radical idea? It's a radical ideal if B is reduced, the ring B. So that's when you get it to be a radical ideal. But now, this is an example to show that it is not always the case that it will be a radical idea. So if we take a ring, so we take this ring homomorphism from A to B, and we let B be a non-reduced ring. And of course, we let VRP have the property that it sends non-zero divisors to non-zero divisors. Of course, an example is given there of an isomorphism, it does that. Then, tau of VRP is not a radical ideal, because this is the argument there. if you take a B there in this torsion ideal, then by definition, the product, this product is equal to 0 for some non-zero divisor U in A. Now, since Varpy at U is a non-zero divisor, it follows that B is equal to 0. Hence, this torsion ideal is equal to 0. But now, this is just the zero ideal. It's not a radical ideal. But of course, if your B is reduced, then it becomes a radical ideal. So this is an example whereby we can show that definitely it's not always the case that Varpy is a radical ideal. There we go. This is just justifying the fact that if B is reduced, then just put the little stories there to see that that is the case. Okay. Here we go. For us to prove one of the main results we have, we did some lemmas. So one of the lemmas is this. If we have a ring homomorphism and A is in A, then read Varpy at box of A is given as this. I said a lot has been done regarding the frame of radical ideals, but I was actually shocked that maybe there is a result somewhere we've not seen, but we never saw this. Yeah, so we decided to just put it in there, just put a little proof that this is how it maps, right? So, which is very interesting and it's very convenient. But anyway, I just put the proof there for completion because it's a little bit longish. So let's go back there. Right, so quality, proof, containment, so proof, but that is what you get. That is the case. Okay, so this is part of the argument that you can actually get at. Aha. So now, we are moving from rings to algebraic frames with fibs. So we're thinking now we need to connect, of course, in a very nice way. Look at the connection between the non-zero divisors in a ring and units in the frame of radical ideals of the ring. Okay, so another result we should recall is that, of course, if you take the products of non-zero divisors in any ring, you get a non-zero divisor. That's going to be very useful. So the first lemma we have, if we have for any ring A, if U is a non-zero divisor, then box of U is a unit in the frame of radical ideals. Aha. To go the other way, it has to be reduced for that to happen. So this is one of the results that we have that we're going to use. Also for completion, I put the proof, which of course we're not going to go through. So I put it there just for you to see how the argument goes. Right. It's not end of it. This is the end of the proof. Okay. So going the other way, this is the argument for it's actually very straightforward how these things work. Now, the idea is we want to compare the torsion ideal that was defined by Picavet and co. Then we'll also want to compare the torsion ideal that we extended. Instead of the zero ideal, we put in the neo-radical. Then also, we want to include that with the torsion element of our frame. In this case, we're dealing with the frame of radical ideals. Something that we need, the definition that we need is in this paper of Pointer, saying a ring satisfies condition C if whenever I is a finitely generated ideal of the ring consisting entirely of zero divisors, then the annihilator of I is not equal to the zero ideal. Okay, so now, in Zuckerberg, he actually called this property A. So these are just kind of like the familiar kind of definition that has been used by some people. So now, in the proposition we looked at in the first, our first result that we looked at, we see that for any fifth frame homomorphism, the set is an ideal of the lattice, the compact elements of M. So now, as a subset of M, we actually see that, of course, it's none, you can deduce from there. So it's merely a directed set because it's an ideal of the lattice of the compact element. So looking at it as a subset of M, it's a directed set. Okay, so this is one of the main results that we have. So given a ring homomorphism, A, we have the containment. That is true. This is contained, so this is always contained in its radical deal. But of course, we look at this containment first. So we look at this containment. This containment is true because this is a radical ideal, and it is the smallest ideal containing, you see, that ideal there. So this follows from the fact that this is a radical ideal of B, so that is fine. Now, we already know that the first containment holds, so we don't need to prove anything here. So the idea is to compare this and the last one. So what will that be? The two lemmas we discussed before, this is where they become useful. So that is what we use in proving that this, we have that containment there. And that's not all. The B part of it, what does it say? If both A and B are reduced and furthermore A satisfies condition C, then you have equality, of course. So here, you have equality there if both of them not just being reduced, but including the condition C that we introduced in a few previous slides. Right, so we know what happens there now. And of course, our T of H being a directed set becomes very useful in proving the B part. So, and also we use the information that in any complete lattice, if a compact element is below the join of some directed set, then it is below a member of that set. So we use this information. Something else we use, already we know this is a unit. So we looked at units, compact and dense. So we also use this information to prove them.
Tiga, do you mean the second one? Do you mean rid of B?
Which one is that?
Just the second up at the top. The first item.
Yes, that's rid of B, that's the typo. Sorry. Of course, it's rid of B. Okay. Right. So here. Okay, so something else that we used, just to put a few things there, is that in a reduced ring, if we have U as a unit, but now we're looking at the compact ones, of course, the unit compact, then the annihilator of U has to be the zero ideal, because just think about it, right? Looking at non-zero divisors, what annihilates them. So it's kind of like an analogous way of looking at it here, where the annihilator of a finitely generated ideal course, is 0 because here we're looking at the compact ones. Okay. Now, I'm bringing back this prime toe definition because I want to use it in a way whereby I kind of like have a very nice way of characterizing them. So here, the prime toe, so the elements that are prime to I is just this set. For every x in A, the product is in I, implies x is in I. We've seen that before. Actually, it's equal to this set. And of course, once you look at it properly, do a little bit of calculation there, you will see that this points here is actually it's a multiplicatively closed set from what we could see. And it follows, we also know that if I take the intersection between the points of I, not prime to, I beg your pardon, not point, prime to I and I, take the intersection is empty. Okay, now where are we going with that? We want to characterize it in a way whereby we can now bring in, you see, so if we have this from the definition that A is a non-zero divisor, even only if A is prime to the zero ideal. Like I said the other time, we moved away, we generalized a little bit more, and we looked at, oh, instead of prime to the zero ideal, we're going to make it prime to the new radical. So this is what we have that is given, writing it nicely in that form. Now, this is what we define, making it a little bit more general. So here we said a ring homomorphism, if a vector from A to B is a ring homomorphism, we define the nil torsion ideal. The nil torsion ideal is to be the set satisfying this. Okay, so now for any ring A, the set of the non-zero divisors is contained in this set of prime to the no radical, which we think is a good result, which is a little bit more general than what they have. And that is the proof for that. Okay, so now look at the relationship here between them. Because you define this in terms of prime to the new radical, automatically you know that this will be a radical ideal, right? So if this is a radical ideal, of course, this containment will follow, but we did some stuff there to show that. We have equality of these two. If A is reduced, then we have equality of these two if A and B are reduced. So this is one of the results, very good results that we have there. How many minutes do I have now?
6.
Oh, okay. So now, here we have, if I have, see, this is a very nice characterization for the units of your ring A. You see, which we thought it was it was good. So now, something else we wanted to look at, because if you look at for reduced rings, if I take any ideal, its annihilator is the pseudo complement. If I take a radical ideal, its annihilator is the pseudo complement. So we wanted to, since we are now defining in terms of nil torsion ideal, let's move a little bit. Let's see if we can get something more general. But of course, luckily, this definition was given by Dube and Picavet in that article there, whereby you can actually generalize a little bit more than just having, if you don't want to deal with reduced rings. So here, we redefine that property C that was given before, and we said a ring A satisfies property C prime if every finitely generated ideal I of A with, you have this set, contains an element which is prime to nil A. Okay. So now, from there, we have this nice result. We have that ring homomorphism. Then we have this containment, and the containment is equality if A satisfies condition C prime. So now I may not have time. Yeah, I may not have time to really go through the Z ideals. Of course, this is an algebraic frame with is coherent. So actually, in a paper, my paper with Warren, we looked at the lattice of Z ideals of a commutative ring with identity. And this lattice is a coherent frame and is a quotient of the radical ideals, the frame of radical ideals. So it's reasonable to start thinking all these results that we have for the radical ideals, frame of radical ideals. We can, what can we get for the frame of Z ideals? So the idea was to think of the frame of Z ideals. Yeah, these are just background story on the frame of Z ideals. And I don't have time now to go through. My time is up, right?
Well, you got 4 minutes, but you can go a little over.
Oh, thank you. Okay, so for the frame of Z ideals, this is how we define them. So you Z of A, actually we were using before myself and Warren worked on this, we were using M. Yeah, but he said no, it's better because zero sets and all that makes more sense to use Z. So we changed everything to Z. So these are just some background on how you look at the frames. But the idea is this. What are the results we get for the frame of Z ideals regarding this torsion ideal? So let's quickly take a look at those ones. Of course, So the functor Z, how does it map? The problem is, you see, for the frame of radical ideals, we do not have any restriction. Rings with identity, you just go down to fifth frame. But with the Z ideals, you can't do that. We have to restrict to morphisms that contract Z ideals to Z ideals. Because once you don't do that, it does not work. Because of missing this paper, prime ideals, prime and Z ideals and prime ideals. He gave a very good result there that actually is the foundation that if you do not restrict, your morphisms are not defined. Okay, so let's see. Here, you see, but one thing we did here for missing, when he was looking at the structure of Z ideals, he looked at it as a semi-prime, semi-primitive ring, whereby in fact they have zero Jacobson radical. But we thought, no, let's move a little bit away, more general. Look at something more than just rings with zero Jacobson radical. So maybe Warren corrects us here because we do not know. So we consider rings whereby the new radical coincide with the zero Jacobson radical. Do they have names? Oh, you don't know. Okay. So we said we call them nearly semi-primitive rings. So these are the things we worked on. So we looked at something, a class of ring that is bigger. Of course, it is obvious that every semi-primitive ring is nearly semi-primitive rings, but going back is not the case. So we actually have an example of a nearly semi-primitive ring that is not semi-primitive. So if you look at Z mod 4, so they coincide there, but it's not semi-primitive. Okay, so now let's just quickly look at what we have here. So for any ring A, these are the compacts. These are the basic compacts, right? Once you write it Z of U, these are the basic compacts. But if I have U, and As a non-zero divisor, then Z of U is a unit here, if and only if. So the characterization in terms of prime 2. So in our case for read, you have the nil radical. But in our case for Z, for read, you have the Jacobson radical. So that's how it works. So some of the results that we looked at there, we have a few of them here. But the proofs are not the same. It doesn't just follow, because remember, when you're dealing with your radical ideals, you're dealing with elements. But with the Z ideals, it's defined in terms of maximal ideals. So it's not like, oh, but some of them are similar, but some of them you have to do a bit more. So it doesn't just follow immediately. Okay. So here, we also have this kind of containment, right? And again, it follows also that this is actually not a Z ideal. Your ring has to be semi-primitive for it to be a Z ideal. And a few other things, I think I'll stop here. Okay, this is the last one. So the compact ones, these are the compact ones. You see how different they are from your radicals. Radicals, you just look at the elements, you are able to get their compact ones. But here, this is our compact Z ideals. So here you have equality here when you put in your condition C. The last one for the condition of C prime, we didn't do that. Why? Because we are considering rings whereby the Jacobson radical and the nil radical coincide. So the last result was not necessary. Thank you very much. I'm sorry for taking my look.
I know. I would encourage you to not use condition C.
Okay.
The last 20 years, nobody's used condition C.
Okay. Right. Okay, so we must go with Hooker.
And A prime.
Okay.
Even the non-commutative.
Okay.
You Google Corey's there.
Okay. I will tell my collaborator that.
Yes.
We actually, it's a property A, but we stuck to C prime. Okay.
Can I ask a question? How did you define the tau again?
Oh, how that's an
I thought that was an element. I thought that was the join of the.
okay. Let's quickly go back there.
I see. So it's an element in the frame of radical like yours.
Correct.
Okay.
Correct. That's what it is. Yeah, but yeah.
Have you looked at rings that don't satisfy property A and like how crazy can that be?
I'm doing this easy, simple stuff. Then maybe, I don't know. Yeah, but we think about that.
Patel has an example. Lucas has ways of using A plus B rings to construct other examples that don't.
Oh,
He has a paper that shows how to construct things that don't have property A.
okay,
So
okay, interesting.
Lucas was a student of Huckle.
Oh, okay.
Oh, geez.
Oh, okay.
Ah, good eye.
Oh, anti-homomorphism of, what are those? Anti-homomorphism, what is that? You don't know? Okay. Tending to, we don't know what that is.
Well, in this case,
I think he can hear you.
Okay,
Yes.
insane. Yeah, just tell him. Okay, hello, Messi.
Hello, excuse me.
Yes,
Yes.
please. Can you
Yes.
tell us what that means?
Oh, yes, I mean by anti-homomorphism, if I have any map T of xy equal T of y, T of x. It's not like it is a swamp of the homomorphism.
Okay, so
Yes,
yes, we've not looked at non-commutative cases.
yes.
So I'm not sure how to answer that because we've not done that. Because all our rings here are commutative.
Mhm.
So that's a good question.
I mean, that's torsion, or like torsion is,
I'm not.
yeah, I don't see this.
Well, all right, anything else?